Okay, Math 1324 students. We're going to talk about section 9.4, which has got the strange title Binomial Probability Distribution, which might seem, where'd that come from? So let's talk about that. All right, so if you have an experiment that always has a binary result, two things, one of which you could decide to call a success and the other one call a failure. And the success has a fixed probability, P, so the only alternative is failure. That would have a probability of 1 minus P. And if you could repeat that, and each time you repeat it, the probabilities are the same, P and 1 minus P. They're independent of having just performed a previous trial, so the trials are independent. If you repeat that n times, then we say that there have been n Bernoulli trials. This is named after a math wizard from the 17th century named Jacob Bernoulli, who was actually being paid to help people in the courts make good bets on rolling dice. Because, for example, rolling a die is a very good example of a Bernoulli trial, right? You roll the die, and you pick it up and you roll it again. The two rolls have nothing to do with each other. They're independent. So if you're rolling a fair die, and let's say we're going to declare success is rolling a 2, right? Then the probability of success on each trial is then a fixed probability P. Here would be 1/6, right? So that's our P value. That's fixed each time you roll the dice. The probability of rolling a 2 is 1/6. Therefore, the probability of failure is 1 minus that, or 5/6. So if you repeat this trial 5 times, a common wager could have been betting a certain amount of money that that person is going to roll that 2 no more or more than 3 times, or no more than 3 times, or maybe less than 2 times. Or how about the probability that they're going to do every time? They're going to get a 2 every time they roll that dice out of 5. What's the probability of that? Or not at all. Actually, those last 2 are the easiest. We can solve those just by drawing some of these helpful blanks, right? And saying, okay, there were 5 throws. The probability of success every time, well, what's the probability of success? 1/6. So 1/6 times 1/6 times 1/6 times 1/6 times 1/6. Oh, that's just 1/6 raised to the 5th. That one we could answer. Or if it was a probability of never getting a success, never rolling a 2, that would just be 5/6 in each of these spots, or 5/6 raised to the 5th. Those questions are easy and don't require any special mechanism. So a much more clever is to bet on something that's hard for people to calculate, right? What's the probability? So in this one here, when I was saying success every time, if I let x be equal to the number of successes, so let x be equal to the number of successful rolls of a 2 out of 5, n equal to 5, total number of trials. And the glare is already starting to affect you guys, so let me move this. I think that's going to help. It's going to at least help with more of it. Okay. So, right, you can see that? Okay. So if we declare x, the number of successes out of n equal to 5, then these other questions, so for example, what's the probability that x, the number of successes, will be less than 2 times out of 5? Well, that means that x, the number of successes, would be less than or equal to 1, right? Less than 2 out of 5 means 0 or 1, x equal to 0 or 1. What's the probability that x equals 1? Or the probability that x is greater than or equal to 4? These questions require some special counting or accounting or a combination of the two, right? So let's duke it out the long way once, and then you'll understand why the necessity for those formulas they provide you in the book. Okay, a little bit of motivation there for formulas. Yeah, so you can read this. Okay, good, the glare is not there. All right. So let x be the number of successful rolls of a 2 of the die, rolling the die 5 times. The probability of x being equal to 0, in other words, no 2's show, well, that's pretty high because you had a 5/6 chance on each roll, and you multiplied 5/6 by itself 5 times, and there's only one way to do that. So 1 times 5/6 to the 5th is 0.4019. Why am I bothering to write down that I'm multiplying by 1? Well, you'll see why in the next question. If somebody's asking what's the probability that you rolled a 2 once out of 5 times, well, maybe on the first roll you had a success, you rolled a 2, and the other 4 were failures. But you could have first had something other than a 2, then a 2, and the others failures. Or it could have gone this way, or it could have gone that way, or could have... How many different ways can you, out of 5, just get a 1? Well, that's the number of combinations of 5 things taken one at a time. Or you could just, if you write it all out, 1, 2, oh, that's 5. Oh yeah, that's the same thing as 5, choose 1. Now, each of those situations is distinct from the others, right? So you could have rolled 1 success this way, or that way, or this way, or that way, or this way. So there's 5 different things that you're taking the union of, 5 different events you're taking the union of, and they don't have any intersection, right? So you end up adding their probabilities. But they all have the same probability, which is 5/6 to the 4th times 1/6 to the 1. All right, 5, 6, 5, 6, 5, 6, 5, 6 times 1/6. There's 4 of the 5/6 and 1 of the 1/6. Same thing in each of the 5 cases. So it's 5 times that same product. Doesn't matter how we write that we're multiplying 5/6 4 times itself 4 times and 1/6 once, right? Multiplication is commutative. So there's 5 of the identical same probability, and so that's how we end up saying, getting you to the formulas, the probability that x is equal to 1 is equal to the number of ways of choosing 1 out of 5 times, now look over here. So we had that, this is the number of successes, right? So we have 1/6, the probability of success, raised to the first power. This other number here is 4. Because there were 4 other tries. Okay, so notice the pattern of the 1s. And by the way, when you calculate this using your calculator, you get 0.4019. So that just happens to be the same as the probability of this, because that's a 5 and that's a 1/6. 5 times 1/6 is the same thing as 5/6 raised to the 5th. Okay, now probability that x is equal to 2. Now we're getting somewhere, right? So now you could have 2 successes at first, or you could have another success in here, or in here, or in here, or you could keep moving the 6. How many ways are there to choose 2 out of 5? 5 choose 2 is equal to 10. You could list them all out, but the problem point is there's 10 different ways you could get 2 successes and 3 failures. Each of these events, each of these 10 events has a probability of 5/6 to the 3rd times 1/6 squared. So there's the 10. 5 choose 2 is 10 of these things. That turns out, because these are a lot smaller, that turns out to be 0.1608. What's the probability that x is equal to 3? All right. So you tell me what to write in here. That's going to be a 10 because I'm going to have what choose what here. What should go here and what should go there? Noticing the pattern? That makes this a 3, and that has to be, for this entire Bernoulli process, that has to still be a 5. And if I could just write a 5 there, that would be nice. Here's a 5. There you go. So 3, 3, and 3. There's 3 successes. So that means there's how many failures? 5 minus 3 is 2. Well, that turns out to be equal to 0.0322. How about this one? The probability that x is equal to 4. So with something choose something, that number is going to turn out to be a 5. What should I write in here? So we had 5 choose 1, 5 choose 2, 5 choose 3. So this is 5 choose 4, which number turns out to be the number 5. And that means because you had how many successes? 4, 4, 4. How many failures then? Just 1. Now, the probability that you had 5 successes, we've already answered that question. That was a success every time. That was equal to 1/6 to the 5th. Well, you'll get the same thing here. You'll get a 1. There's only one way to do that. If you had written 5 choose 5. 5 successes. So that means you would have, which turns out to be a 1, times 1/6 to the 5th. And that means there was a 5/6 raised to the 0 power in there. 5/6 to the 0, anything raised to the 0 is just a 1. All right, so see these numbers in green, 1, 5, 10, 10, 10, and 10, and 5, and 1. Those numbers come out of a pattern you might have seen before. It gets called Pascal's triangle. Pascal was another whiz back from the 17th century in France, but actually there are transcripts that show in India they had this idea 1,000 years before that. So I don't know why we still keep calling it Pascal's triangle. But the pattern, the way to generate these numbers is to put a 1 here. 0 plus 1 is 1, 0 plus 1 is 1. Now if we go to the second row, we have 0 plus 1 is 1 again, but 1 plus 1 is 2, 1 plus 0 is 1, and so on. You can see that these numbers in between are always the sum of the 2 above them. And if you carry this down to the 5th row, counting this as the 0th row, you're going to see the 1, 5, 5, 10, 5, 1. 1, 5, 10, 10, 5, 1 that we saw up here. What's going on? Well, when Pascal was looking at this pattern, he was explicitly saying, look, these are the coefficients, the binomial coefficients I get if I take the binomial expression x plus y. If I raise it to the 0th power, I just get a 1. Anything raised to the 0 power is 1. If I raise it x plus y to the 1st power, I get 1x plus 1y. There's your 1, 1. X plus y squared gives you a 1, 2, 1 for binomial coefficients. X plus y cubed would be 1, 3, 3, 1, and so on. So the 1, 5, 10, 10, 5, 1 are the binomial coefficients from x plus y raised to the 5th. And so this name, gets associated with this kind of pattern. And so that's why if we look at the probability of getting x equal to 0, 1, 2, 3, 4, or 5, and put it in an array like this, can you see that? Trying to get rid of the glare. I'm not sure where that's coming from. All right, let's try. Can you see? No. Can you see this? So right here, a little bit of glare, no glare unless I touch it. So if we take the number of successes out of 5, 0, 1, 2, 3, 4, 5, because you can have 0 successes, right? the probability of each of them. Probability of 0 success, well, that was 1 times 5/6 raised to the 5th power, right? That could have been written differently as, let's see, C5 choose 0, that would give me a 1 times 5/6 raised to the 5th power and a 1/6 raised to the 0th power. That is the same thing as that. How about for 1? What do we have? Well, according to the formula, that should be the number of combinations of 5 things taken once. 5/6 is going to be raised to some power. But the 1/6, we can see, is raised to the 1st power. So since these, the sum of these two represents the fact that there were 5 rolls, this has to be a 4. Okay. And so on. Let's move these lines a little bit. There we go, a little bit more equitable. So in each of them, how many different ways can this happen that you get x equal to 2 successes out of 5 rolls? Well, 5 choose 2, 5/6 raised to the, you finish this, and then come back, check to see if you have the same thing. This should be a 5/6, well, how do I get it? First of all, just make sure that the 1/6 probability of success is the same thing as this number, and then n minus 5, that 2, n is 5, minus 2 is 3. This should be this. 1/6 has to be raised to the 3rd power, so 5/6 has to be raised to the 5th 6th power. Okay, so after a while, you get the pattern, and it's just tedious to write all this in here. Right? What should I be writing up here? A 4. Therefore, this is a 1. And finally, this last one, 5 successes out of 5 rolls, no 0 failures times 5 probability of 5 successes. Okay, and you can go to the calculator because you can easily find these combinations quite easily. You could multiply all that together. But there is another way of doing this. All right. So these numbers, by the way, I had written them down. Let me just bring them up here. What these turned out to be approximately. So these numbers were approximately 0.419, 0.4019. Again, that's coincidence. For 1, it was 0.49. For 2, it was 0.1608. For 3, it was 0.0322. For 4, it was, what was that one? Well, let's see. So that's a 5 times a 5/6 times 1/6 raised to the 4th. Let's say if you want to calculate that one number, but not necessarily by working through the formula and multiplying it all out. Let me show you how to use your graphing calculator to do that. Okay. Alrighty, so let's see if you can see this without a glare. Looks pretty good. Okay, so on your graphing calculator, we are going to find a button that talks about binomial probability distribution. So there is a place where all the distributions of the different probabilities functions are listed. That's under distributions. If you could see that, but that is in blue. So we press second function, distributions. And it's giving us a whole bunch of distributions. Normal, we might get to normal next week. binomial probability distribution function. That's binomial PDF. Okay. So if I want to, for example, this one here, probability of x equal to 4 successes out of 5 trials, where the probability of success is 1/6, then I pick binomial PDF. This calculator is a little bit more modern. It breaks it down for me and asks me questions about what those quantities n, p, and x are. And then I plug them in, and then it pastes them in. You'll see in a minute what it's going to look like on an older calculator. So number of trials is 5. The probability is 1 divided by 6. A probability of success, that's little p. And x, the number of successes out of 5. If here we're taking it to be 4, that should be a 4. And then you go down to where it says paste. Now it's going to stick it into the binomial PDF function the way it looks in the older calculators. Trying to make sure you guys can see that. Okay, so it's binomial PDF parenthesis n comma p comma x. And that's what your book's trying to tell you about in that section 9.4 on its technology tip. So you get that loaded in there, you press this, and you get 0.00, go to 4 decimal places, that's usually safe, 0.0032. 1, yeah. So this one is approximately 0.00321. Notice that that's about 1/10 of the previous one. So that comes up here, 0.00321, right? And for the 5th one, we already calculated that. That's 0.000128. So now we have here a distribution of probabilities, okay, using the binomial probability, so-called because of the binomial coefficients. And if you add up all of these, the sum of the probabilities on this one, because I've been rounding and so on, the sum of all the probabilities here is going to be 1.123. I think that's what it turned out to be. Just a little bit over 1, but that's because of rounding, right? And those are disjoint events. So that is a nice probability distribution function. Okay, so that's all good. Now let's get back to some of these more complicated questions that get asked of you, right? So for example, what if somebody says, what's the probability that the number of successes, what's the probability that you roll a 2 more than 3 times? Okay, so if you want to say x is more than 3, the probability that x is more than 3. I'll look back up here at the distribution for a minute. Okay, so here's for 0, 1, 2, or 3 successes. But they're asking what's the probability that's more than that. So that means they're saying what's the probability that x was equal to 4 or x was equal to 5, right? Those are the only 2 possibilities other than being 3, 2, 0, 3, 2, 1, 0. More than 3, strictly more than 3, means you're talking about this one or that one. All right, so we would rewrite that inequality here as that's the probability of, x. That's the probability of x being greater than 3, greater than or equal to 4. Well, that's the same thing as the probability that x is equal to 4 plus the probability that x is equal to 5. So at this point, it looks like we have to calculate each one of those separately and then add those 2 numbers, right? You could, if you had the probability distribution in front of you, just say, okay, that's this plus that, and be done. However, What if they had asked, well, let's go back to one of our other original questions. What if they ask, what's the probability that you will roll it to fewer than 2 times? Fewer than 2 times. Well, that's the same thing as this. The probability that x is less than or equal to 1, right? Fewer than 2. So if you're fewer than 2, here's 2 and above. Fewer than 2, that's x equal to 0 or x equal to 1. That is the same thing as saying, what's the probability that the number of successes is less than or equal to 1? Well, now we have something other than just calculating the sum of those 2 probabilities if we have the probability distribution in front of us. Now we can use something called binomial CDF. That C stands for cumulative. And if I write NPX in here, if I write 5, 1/6, 1 in here, binomial CDF adds up all the probabilities of x being equal to that number there or any less. Okay, so I can go to binomial CDF. It's a handy tool. Again, trying to make sure that you guys can see this screen. So second function, all right, let's get that on. So let's see. So second function, distribution. Go down to binomial CDF, not PDF. Enter that. This more modern one makes it into a menu. So the number of trials was 5. Probability of a success is 1 divided by 6. The x value that I'm putting in here is 1. It's saying, so I'm accumulating all the probabilities up of successes of size 1 or below. And this is going to paste them in there. And I'm going to get 0.803755. All right, so this is 0.803755. Is that not the same thing we would get if we just had all the probabilities in front of us and added these 2 numbers? All right, 0.4019 added to itself is 0.8038. When you round this one to 4 decimal places, you get the same. All right, so hopefully that helps you get started on those problems.